We learned a couple properties about the matrix transpose a couple lessons ago, and these properties also apply to the matrix inverse. So let's review those and see the new versions with the matrix inverse. So first of all, let's recall how the matrix transpose works. We have a matrix, say 1, 2, 0, 3, negative 1, 2, negative 4, 4, 1. And take the transpose of that. We sort of draw a dotted line down the diagonal and flip the matrix on the dotted line. So 1, negative 1, 1 stay in the same place. These 2's and the 0 go below the diagonal, and the 3 and the 4 go above the diagonal. But recall that we said if we want to transpose a product AB, then it's the product of the transposes, but we have to take that product in the opposite order. And more generally, if we have a product of K matrices and want to transpose that, then we take the product of the transposes, but in backwards order again. So the inverse, A inverse of a matrix A, if the inverse exists, and we know that not all matrices are invertible, satisfies similar properties. If we want to take the inverse of AB, it's the product of the inverses. That is, if A and B are both invertible. More generally, if we want to take a product of matrices and invert that, so the inverse of P1 through Pk, that is the product of the inverses but in backwards order. So these rules work just like for matrix transpose, and they're pretty easy to see. To see this, we can just multiply. So the inverse of the product P1 through Pk is the matrix which satisfies the matrix, let's say B, which satisfies B times P1 through Pk equals the identity. So if we just try this with the matrix I proposed, we'll see that we get the identity. So we'll write Pk inverse, Pk minus 1 inverse, etc. So I think this should invert P1, P2, etc. up to Pk minus 1 Pk. So when we multiply those together, what do we get? Well, the P1 inverse and the P1 cancel, and that gives us the same product without the P1s in the middle. And now P2 inverse and P2 are next to each other, and those cancel. And every time we cancel a matrix and its inverses are next to each other, then the next two are inverses, and the next two are inverses, and we eventually cancel everything. So this product of inverses backwards times the product of matrices forward does give us the identity. This therefore is the identity, this therefore is the inverse of that half. Now also recall that if we take the transpose of a matrix, we just get the matrix back. Matrix inverse satisfies the inverse of A inverse is just A, just like the transposes. And the reason is that A inverse inverse is the matrix that undoes multiplication by A inverse. So let's say we start with M, multiply by A inverse to get A inverse M. To undo this, multiply by A. So A times A inverse times M. Now the A and the A inverse cancel each other, and that just gives us M. So indeed A is the matrix that undoes multiplication by A inverse. All right, now we have this natural question that involves the transpose and the inverse. What if we want to invert A transpose? Assuming A is invertible. And the easiest possible fact is true. The inverse of A transpose is just the transpose of A inverse. So if you know how to invert A, you also know how to invert A transpose. Just invert A and take the transpose of it. So let's suppose A is invertible. Then A inverse A is the identity. That's what it means for A to be invertible. Let's transpose both sides. Now we have A inverse A transpose equals I transpose, which is just I, because the identity matrix is its own transpose. On the left-hand side is when we take a transpose of a product, that's the product of the transposes, but in the opposite order. So we have A transpose A inverse transpose equals I. So that means that this matrix must be the inverse of A transpose. In other words, A transpose inverse is A inverse transpose. The end.